Hi Prabha, let's wait for a few more minutes, then I think we can start, in case anyone is joining. Hi, yeah, good evening. मीट में मेरे को कनेक्ट करना है। एक मिनट रुको शायद। Hello everyone. Hi, I am Ayush. I am PhD student at IIT Delhi. I am TAing for this course, and in today's session, what we'll be doing is like we'll be primarily focusing on problem solving. There was suggestions from last session that like we should focus on problem solving as well. Uh, and there were concerns about even the gradient computation and other things were there. So what we have done for this session is like we'll be looking into gradient computation and some basic CNN questions, and then we'll review the assignment one, which was due on 19th, right? And then I think we can look we can spend some time on edge detection kind of frameworks which are there in Python, and maybe we can link how deep neural network perceive these filters. So deep neural network also learn this low level filters on their own, right? Like to extract out information. So and so like the initial layers basically learn that. So we will try to connect that. So I think we should get started with our problem solving session. So the first, so this content is basically derived from CS 231 Stanford lectures, and like if anyone has gone through it already, it might not be very new, but if for the people who are like looking into it like for the first time, it's like a very good way of understanding the basic concept. So whenever like I learned using these from these lectures only. So I find them very intuitive and like very easy to understand. So as you know that whenever you are doing like any like whenever you are building any neural network, you can basically represent it as a computational graph. So like if you are like building up a function f of x, which is like dependent on x, y and z, and the function is like x plus y whole bracket z. So if you want to represent this function, what you can do is like you can basically write it in a form of a computational graph where the x and y are added, then it is multiplied with the z. And like suppose x has a value of -2, y has a value of 0.5, and z has a value of -4, right? Let us assign a value q to this intermediate addition, right? So x plus y is basically 3, and what we do is like we do a multiplication of z and q to compute f, and the value comes out to be -12. So this is, assume that like this green is a forward pass, right? And the goal is like how do we compute the backpropagation gradients so that like we can update the variables, right? So we what we are trying to do is like we are computing uh, with respect to x, f derivative of f with respect to y, and derivative of f with respect to z, right? So the intention is how to identify how does f changes if there's a change in z, or if there's a change in y, or any change in z x, right? So like you, for that you should know there's something called the chain rule, right? So whenever I am computing f of derivative of f with respect to x, it has, I can write it as derivative of x f with respect to q, derivative of q with respect to x, right? This is the path I'm taking, this is the path I'm taking, right? Q, and then I'll move in this direction, right? Okay. So how do you write f? F is basically q into z, q is basically x plus y. So derivative of q with respect to x is basically, any guesses? One, right? Derivative of q with respect to y is also one. Derivative of f with respect to q is z, right? So let's just feed in the values here. So what we are trying to do is like we are trying to compute f of derivative of f with respect to x. So this term is basically 1, and this term is basically z. And what is the value of z? Z is -4. Makes sense, right? Hello, am I audible? Okay, okay, great. Similarly, like suppose if you want to compute how the output changes with respect to y, what you do is like f of q with respect to y. Similarly, it comes out to be 1 because a derivative of q with respect to y is 1, and like derivative of x with respect to q is z. So in both the cases we have -4. So right. Similarly, what we want is derivative of f with respect to z, right? F is directly dependent on z, so that's why we'll do is like we'll just uh, check derivative of f with respect to z is basically q, and q is 3, right? So it is q which is equal to 3. Makes sense, right? Anyways, so uh, like now what we have done is like we have computed these derivatives, right? uh, like for this is q is z also. I'll just say here, I'll just write -4. Can you see a pattern here? Can you see a pattern in this point, at this point, right? Let's just analyze. So what we do is like whenever there is a multiplication operator, right? In those cases, the derivatives are kind of reverse, because if you see the derivative, so the value of q was 3, and derivative of f with respect to z is 3. Similarly, uh, similarly z is equal to 4, and derivative of f with respect to q is -4, right? Whenever there is an addition operator, the same derivative has been passed to both of them, right? -4, -4, -4. So this pattern basically is persistent in many places, right? So like whenever there is a derivative, it's kind of a like you switch the gradients, right? And whenever there is a addition, you pass the same gradient in the backward direction. Make sense? So moving on to another like example. I mean, if you have doubt in this question, I think it's good time like to speak up. We can discuss, and if it is clear, I think we can move to next example. Um, Not affect. I mean, but like it's good for understanding. Yeah, so like this pattern you observe in most of the cases. So it's good for understanding. Whenever you're doing back propagation, it will not affect. Yeah, yeah. But I don't understand what do you mean by the effect? Uh, no, no. No, 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 no. I mean, this is just for the observation. Yeah. So, I mean, uh, no, it will be for the pattern is consistent. So, for other examples as well, it will be there. Yeah, but whenever you're doing back propagation, you're doing the gradient computation. I mean, you have to do it for every node. But like if you observe, this pattern will be like you can see this pattern. Yeah. So in another example, let's say like you have a function which is like dependent on w and z, and what you're doing is like we're kind of taking a sigmoid of w1 w0 x0 w1 x1 and w2, right? And how do you write it in a computational graph? You have a multiplication of w0 and w1 here and here, right? You have multiplication of w1 and x1, and you have w2 which is independently represented, right? You do a multiplication for both of them, you did addition, right? And you finally add w2 in this case. Then what you do is like you do a multiplication with minus 1, you have multiplied, you do a exponential here, you have added uh, plus 1 into it, right? And then a inverse operation, right? So it's 1 upon everything. So that's how you create a like a forward pass or a computational graph, right? This is the final value you will get after a forward pass. So these are the initial values. So w0 is initialized to 2, x0 is initialized to minus 1, w1 is minus 3, x1 is minus 2, and w2 is minus 3. Whenever you multiply, you get minus 2, 6, and your addition is 4. Then like the forward, and then everything follows. So let us look at the some of the operation we might need. So if the function is exponential of x, e to the power x, the derivative is e to the power x. If the function is ax, the derivative is a. If function is 1 upon x, the derivative is minus 1 upon x square. If function is c plus x, the derivative is basically 1. So c is basically a constant. So at every step what we do is like we have a like one gradient which is coming from the output and one gradient which is corresponding to this node. So this you can call as the uh, local gradient, and one is the global gradient. This is a local gradient and this is global gradient. And this you multiply a local gradient with the global gradient always, right? So let's think step by step, right? So output with respect to output is 1, right? So what we do is next is you have a node which is 1 upon x. So if you want to compute a gradient of 1 upon x, what you do is like minus 1 upon x square, right? So what you do is like you have minus 1 upon x square and you have a value of 1.37. So it's like minus 1 upon 1.37 whole square, and 1 is coming from here. So you have the gradient value at this point is minus 0.53. Make sense? Okay. Next, what you're doing is like we are basically adding one to it, one to our overall operation. So which is best suitable for the c plus x, and the gradient is basically 1. So what will happen is like same gradient passes, right? So 1 into minus 0.53. So the gradient here at this point is minus 0.53. The next is the exponential operation. So when you do an exponential operation, the derivative is also exponential. Right? What we do is like we do e to the power minus 1. The minus 1 is coming from here, and the gradient, which is the global gradient, which is coming back, right? And the value come out to be minus 0.20. This is the value. Now what we're doing is like we're moving one step backward. You have minus 1, which is multiplied, and whenever there is a multiplication, what you do is like a to ax, right? And the derivative is the derivative a, which is the multiplicating factor. So in this case, what we are doing is the local gradient is basically the multiplicating factor, that is minus 1, a global gradient which is coming, and you have the updated gradient at this point is minus 0.20. Sorry, 0.20. Now we are at addition operator. And earlier what we have seen is like in the addition, the gradient, same gradient is passed to both the edges. So here also is addition, here also is addition. Right? This is the first additional operator. So what we have done here is the same gradient of 0.20 has passed to both the edges. So the gradient at this point is 0.20, here the gradient is 0.20. Similarly, the addition is also present at this point. So the same gradient will pass here, same gradient will pass here, right? So at this point, the global gradient which is coming is 0.20. In this branch as well, it is 0.20. Now we have a multiplication factor. So what you need to do is like you have to compute the gradient with respect to W1 and W2. And here as Z, suppose this is the Z, then Z is basically dependent of W1 X1. So when you compute gradient with respect to X1, what you do is like you multiply with W, and when you compute gradient with respect to W, you multiply with the other entity. So what you do is like you have the gradient at this point 0.20, x0 has value of minus 1, you multiply it and pass it to the other branch. It is 0.20. Similarly, for the other branch, like the value is 0.20, you multiply with 2.00, the gradient is 0.40. Similarly, you can actually extrapolate to this step as well. Yeah, so what you do is like minus 0.40, and here I think it should be 0.2 and 0.3 minus 0.60 something. I mean, you don't have to like remember that like whenever there's a multiplication you do like the cross multiplication, but these patterns are basically like present in many cases, so you can actually make use of them. You don't have to explicitly compute the gradient. So suppose you don't know the gradient, what you say, this pattern, what you do is like you have the gradient at this, like let's say the output at this point is z. That is basically the multiplication of x0 and w0. And when you do output with respect to input, you get x, you do you get w, right? So what you do is like you just multiply the global gradient with the local gradient. Does it make sense? Hello, am I audible? Okay, okay, okay. Okay, I hope I'm audible. Great. Okay. So like what you can do is simply like use the sigmoid gates, and what like you should be able to directly bypass this whole step, right? So I mean, the best way whenever you're like stuck in like forward or the backward path, just like create a computational graph and try solving the gradients by hand. So the computational graph will actually help you like to get a sense of how the gradients are flowing. I mean, when you're working with the larger networks, it becomes very difficult. But definitely, like whenever any novelty we are doing and like you want to do some like gradient manipulation, these kind of practices help, and definitely it's good to know as well. Okay. Okay, so next we are moving to like just summarizing whatever we have seen. Like suppose this is your for like computational graph, right? So what you're doing is like you have x as the input, you have y input, w and z as the input. So there are multiple operators. So you have multiplication operator, addition operator, you have max operator. So just think of it as the max pooling. So what you do is like you take the maximum value which is coming as the input. So you have two value inputs, and you what it does is like just take the maximum value. So in this case, suppose 2 and minus 1 are as the input. What it outputs the maximum value of out of these two, so that it will output 2 in this case, right? And you have the multiplication operator into 2 operator. So suppose in the addition operator, you just see that like the same gradient has been routed, so it's kind of a distributor. So gradient addition operator is basically a gradient distributor, so it routes the same gradient in the both direction. So any guesses on what does the max operator does? Anyone? I mean, max is the array value, no, right? Maximum is basically uh, like it can be right, it can be array value, but uh, what how does the back propagation takes place from the max operator? That's what I'm curious. Gradient equal to 1, no. So what it does, it like it pass on the grade. I'm just curious, like how does the gradient backpropagate through the max operator? So let me just answer it. So what happens is, like whenever you have an incoming gradient of which is 2, the max operator, what it does, it routes the gradient to the direction which has the maximum input, maximum value of the input, right? So the same value has been routed to here, and in the other branch the gradient is 0. So what's happening here is, like you are kind of updating the values, the maximum values we are getting, which is basically meaningful for the what do you say, the neural network. Suppose there you have a CNN based network, and you are doing a max pooling operation here. So there can be multiple regions. Like suppose there are four. You can actually split the image into four grids, and you're taking the max grid out of these four, right? So maximum is basically giving you in the more information. So because the activation is higher at that point, right? Suppose this is the leftmost top and leftmost corner. So what is happening when you're back propagating, you're kind of updating this top left grid, right? And you keep the others like intact, because you are not bothered about them. So you ensure that like you get good features from that grid. That's what max operator does. So it routes the gradient to the grid which is basically feeding the input. So in this case, z is has a value of 2 and w has a value of -1. So the gradients are routed toward z because the value is more, because that's the maximum value, right? So the max grade is basically the gradient router. What about the multiplication gate? So what multiplication gate does is, yes, yeah. So it's kind of switches the gradient. So what happens is, like this 2 is coming at this point. You have the in value 3 here, value y has a value of -4. What it does, it multiplies this value with -4 and place it here. So x into z. So suppose this is z is equal to x into y. You compute the gradient with respect to x, so you have the value y, right? And when you compute gradient with respect to y, you have the value x, right? So that's why what you're doing is, like you're kind of switching the gradients. So that's why whenever you're traversing through this branch, I'll multiply this global gradient with the value of -4. So -8 in this direction. Whereas when I'm moving in this branch, I'll just multiply 2 with this value. You have the gradient of 6. Make sense? Yeah. So I mean, like three of the main operators. One is basically the multiplier. So it basically switches the gradient. Addition operator, it is kind of a distributor. The max is a router. Basically, it routes the gradient to the direction which has maximum input. So I think these 3 points should be like you should know these 3 points. Apart from that, the chain rule is essential. Whenever you want to like compute the gradient of output with respect to input, you just apply some sort of a chain rule. You have with respect to x, there are certain with respect to qi. You can have qi with respect to x, and here the I can be from any, like I can be 1 to any big number, right? Like you can have multiple layers in between, right? So the chain rule works efficiently if you want to compute the gradient of output with respect to input. And what does actually the gradient means? So gradient is like how does the output changes whenever there is a change in the input. So what you want is like whenever we are training a neural network, we want the loss to be minimum, and we want our parameters to come to a value which minimizes our like the loss function. So but it, at every step we compute the gradient to see like how the output is changing with respect to the input, and you update your weights in the direction which is kind of minimizing your loss function. So there are two steps. One is gradient computation, and then there's the update step. So uh, so whenever you are like writing a model, some sort of loss dot backward actually computes the gradient, and you have a optimizer dot step basically update the gradient. Okay, so let's take one more, I think last example in this like gradients. uh, Suppose what you have is a convolution network. You have a loss function which is we are computing MSE loss between like the ground truth value and the predicted value, where the prediction is based on W1 W2, and you have the intermediate like outputs which is coming from max pooling and the relu layer, and you have, this is I think the bias term. uh, so V1 is basically max of Z1 Z2, and V2 is basically max of Z2 and Z3. So the question what they're asking here is how, like what is the effect on the loss with respect to Z1, right? This. So any guesses, how do we go about it? And additional information what they have given is you have uh, loss derivative of loss with respect to v1 is given to us. Like we are kind of at this point, it is delta, and what we are saying is like what is the effect of on this delta with respect to these inputs x1 x2 and x3. So we have to operate in this space, because you already have the information about it. So the changes with respect to v1 is delta 1, changes with respect to v2 is delta 2, and we are operating at this stage. So it's basically a max operator, right? So max operator, you have taking input, uh, two inputs, right? Z1 and Z2. This max operator is taking two inputs, Z2 and Z3. So how does the gradient backpropagate? So that's the question, right? So in this point, what we do is like we make an assumption that like uh, sup- suppose this x z1 has the maximum value. So the gradient will backpropagate in this direction if z1 is maximum of z1 and z2, and 0 is basically for z3, but in this case there is no input. So if the z1 is maximum between z1 and z2, the gradient will directly backpropagate in this direction, right? Similarly, if for Z3 effect on Z3, this one, if it is it is maximum between Z2 and Z3, the gradient will back propagate in this direction. For Z2, what will happen is Z2 is basically dependent on, like it's basically like the Z2 has been fed to V1 and V2. So both V1 and V2 are dependent on Z2. So what will happen is whenever there is a merger, so the gradient will accumulate from both V1 and V2. So you have delta 1 which is coming from V1, you have delta 2 which is coming from V2, and you have an addition of that. In the case where Z2 is greater than Z1 and Z2 is greater than Z3. Otherwise it will only pass through one of the branches, because if this this Z2 is not greater than Z3, it will only have accumulate gradient from V1. If this Z2 is not greater than Z1, it will accumulate only the gradient from this direction. So it's kind of a accumulator branch where the gradients are accumulating from two different sources, so V1 and V2. Yeah, I know it might be like a new thing, or like maybe might not be that clear from the first go, but like I mean, give it a thought. I mean, it clear out many things. Like so, yeah. Okay, so let's move to the scene-based architectural problems. So, what we are doing here now will be like we will be looking at like suppose like the CNN-based problems. Like suppose you have a like you are basically designing architecture. In some cases what will happen is like you have to design what is the next size of the next layer, like what size do you want in your next layer. So based on that you should be able to see what is the padding and the what is the slide you require, so that like you can have the exact same output you require in the next layer. So the question what we are solving here is like suppose you have input dimension which is 32 cross 32, right? So what will happen is if we do a convolution operation on it with a kernel size of 5 cross 5 cross 1, because 1 is basically the number of like channels, and there are 10 such kernels like that. What should be the output dimension if I multiply my input, that is 32 cross 32 into 1? Any guesses what it should be? So you have a padding of 2, stride of 1. Okay, let's go ahead. So like for this what we do is like wn is basically the input dimension, so you have it is 32. W padding is basically you have a padding of 2, you have a kernel of 5, you have a stride of 1, this is something which we add, right? So in order to get the output dimension, this should be the case, right? And you're doing padding on both the sides, right? So it is into two, so on the both the sides you're doing the padding. So what will happen here is do what you do is like you have 32 as the input, you have k is the like 5 as the kernel, and this is the padding. So basically padding is basically 2 times the padding. This is your stride and this is the additional uh, factor. So the output turns out to be the 32 itself in this case, right? 32 comma 32 and 10, because there are 10 filters, right? So the output dimension becomes 32 cross 32 cross 10. And how many parameters we have introduced in this case? So the number of parameters are 5 cross 5 for, so 25 parameters for filter. We have introduced 10 such filters, right, into 10, and each filter has an additional bias plus 10. So total number of parameters are 25 into 10 plus 10. Because in CNNs only the filters are learnable, right? Each filter contains, suppose it's a 3 cross 3 filter, so it contains weights w1 w2 w3 to wn, and all these weights are learnable, right? If it's a 3 cross 3 cross 3 filter, so 3 cross 3 cross 3, we have 27 parameters. Similarly, in the next step, what we do is like we do a pooling operation. So what we do is in a pooling operation, we have a 2 cross 2 filter and we do a pooling. So suppose we are doing a max pooling operation. What we do is like we will take the maximum value out of this grid. Only one value, right? So that's why the size of this size reduces to half whenever we do the pooling. So 32 cross 32 cross 10 becomes 16 cross 16 cross 10. And there are no parameters which are learned whenever we are doing pooling operation, because we are just extracting out the maximum value. Suppose we do a CRN based like convolution operation with filter size of 5 and there are 10 such filters. In that case, what will be the output size? 16 minus 5, padding is 2, plus 4 divided by stride is 1, right? So what it should be, 16 minus 1 plus 1, 16. So it should be 16 cross 16 into 10. And how many parameters should be there? You have 5 cross 5 kernel, you have 10 such kernels, and each kernel has the filter has a bias. So you have the same amount of parameters you are learning. Again, 16 cross 16, you have the same parameters. Yeah, so in this case, not same actually. You are basically, you have the number of channels is 10. Earlier it was 1. So the filter size is 5 cross 5 cross 10, and there are 10 such filters. Yeah. So this is the filter size, and there are 10 such filters, number of filters. And this is the number of parameters in each filter. This is biased. So I think, yeah, I also made a mistake here. Like in this case, the channel number of channels was 1, but now when we are feeding this input, the number of channels is 10. So that's why you have a filter which should be of dimension 5 cross 5 cross 10. Make sense?
Yes, sir.
Okay, okay, great, great. Again, if you do a pooling operation, we basically like half the size, and then what we do is like you can actually feed it to a fully connected layer which will be outputting 10 classes, right? And what is the size in this case, the number of parameters, basically you are projecting this to 10. So this is 8 cross 8 cross 10, and you're projecting it to 10. So you have this many connections. So this is the number of parameters you're learning, and for this 10 you have additional bias term as well, right? So that's why the 8 into 8 into 10 into 10, this is also included in the combination. These are the number of parameters, and additionally you have bias term. Make sense, right? Yeah. So next, I think I'll be talking about the receptive field of the CNNs. So I think in the assignment as well, there was one question about the receptive fields of the CNNs. So what will happen is, just think that like you have a input image, and you have a kernel which is of size 5. So there are 5 such blocks which represent it overlaps on 5 such blocks, and you have a stride of 2, and this maps to this block, right? So when you do like slide of 2, you miss, you move this by 2, and the output is at this point. You the outputted value is like presented here. Similarly, if you do a slide of 2 again, so overall 4, you do, the output value is represented here, right? So now for these three values, what should be the receptive field is something which we are asking. Receptive field means that how much of the region in the input space these uh, three have seen, these three filters correspond to. So this will be active when these five blocks will be active. This will be active when these 5 blocks will be active. This will be active when these 5 blocks are active. So effectively it has seen something from here to here. And if you want to put it into some sort of a formula, then k, so this is 5 is basically the filter size, 2 is basically the stride, and 3 is basically number of the adjacent neurons. We can actually generalize it into this form. So the receptive field for any m adjacent neurons in the previous layer is, can be given using this formula. N is equal to k plus s into m minus 1, right? Suppose m here is 3, 3 minus 1 is 2, slide was 2 into 2, this is 4, plus the kernel size is 5. So 5 plus 4 is basically 9, and what is the receptive field we are able to see? It's 9. Similarly, if you move in this direction as well, like suppose now looking at this region's receptive field, it will be 9 in the vertical direction. So 3 cross 3 with this formulation has a receptive field of 9 cross 9.
Sir, what is the utility of this receptive field? What physical or logical significance we can draw from this?
Okay, I mean, I'll come back to this. I mean, there are two significance. That's what I say. First one is what people generally do is people generally have smaller filter size. So what people generally do is like they have a filter size of 3, but what they do is like but what they do is like they make their architectures deeper. So instead of keeping the filter size of 5 cross 5 or 7 cross 7, 5 cross 5 or 7 cross 7, what people generally do is like they use 3 cross 3 filter and make uh, it as a multiple layer. So what will happen, it like, so suppose there are 3 layers, the neuron at the third layer will be seeing a receptive field which is similar to when you are doing a filtering on 7 cross 7 kernel. So it basically saves the your what do you say, number of parameters as well.
Okay.
Right. Plus you need to understand like whenever what is the what is the input uh, features a filter is looking into whenever it is triggering. So suppose in this case this 3 cross 3 block is basically looking into 9 cross 9 features.
So this will be kind of dynamic update depending on this receptive field coming across. Accordingly, dynamic computation can be done in efficient manner. Will
uh,
it help that way?
I mean, I don't understand what is the dynamic computation. Just can you just clarify?
Yeah. Suppose this receptive field, if this value keeps changing, then will the neural network do some dynamic scheduling to optimize the computation in order to save time and faster convergence?
I mean, it's not dependent on the architecture, but on the architect. So when you are basically designing networks, what people generally do is you keep your kernel smaller, but you make your networks deeper.
Okay, so
So
that means in beginning itself, this receptive field can be decided for making better architecture.
yeah. So what people generally do is instead of taking a bigger kernel, so you do multiple smaller kernels. So you have like a deep architecture which has the same kernel size of 3 cross 3. So I think there was one paper, I guess. Maybe AlexNet or I think ResNet. I think ResNet was the first paper which made this claim. I guess maybe I'm wrong, but this was the first paper which actually showed that like all the layers having the same convolution kernel size, but making it much deeper has the better effect rather than like going with the larger kernels and different size kernel in different images in different layers. So what will happen is like the 5 cross 5, suppose there's a 5 cross 5 kernel and you have you make two layers with 3 cross 3 kernel, you make the overall number of parameters lower, but what you're doing is like you are actually capturing the same receptive field as the 5 cross 5 kernel.
Okay, sir.
Yeah, so it basically overall made reduce the number of parameters, made learning faster. So yeah, that's the overall summary of this. So I'll just I should draw it for you. So suppose you have a 5 cross 5 kernel, so total number of parameters are 25. You can actually achieve the same receptive field using 3 cross 3 kernel and then a 3 cross 3 kernel. So in the 3 cross 3 kernel you have 9 parameters here, 9 parameters here, so total are 18 parameters. You are still saving a 7 parameters in this case. It will be like when you move to much deeper layers, you will see that like this number of parameters we are saving compounds, and you are able to have a same learning capacity but with lesser number of parameters.
Finally, it is means faster computation and faster learning, means efficient learning
Yes, yes,
with a buff receptive field.
yes, yes.
Thank you.
Yep. Yeah, similarly, right, like, so whatever we have seen is only one layer, right? So if we can move the same thing into two multiple layers, so here it's the output of 3 cross 3 kernel and a slide of 1, so it will be looking at this region, right? And what these values be looking into, so it has a kernel size of 5 and stride of 1, it will be looking at much bigger values, right? Oh, sorry. Right, so you, for this neuron, you have a receptive field of 3 cross 3 in one, if you move one step behind, and you have a receptive field of 7 when, if you move, uh, should be 7 cross 7 if you move one more step behind, right? So if you can see, uh, if you can do a like quick computation of number of parameters we are using, right? So 7 cross 7 has 49 parameters, right? But whatever what we are using is 5 cross 5, and so 5 cross 5 and 3 cross 3, so 25 plus 9, we are basically saving some of the parameters, right? So that's the whole concept of receptive fields. Okay, next I think we will look at the assignments, assignment which was given, and if you have any particular doubt you can ask, otherwise I'll just go over all the questions, like, right? Okay, so this was question number 1, where we say that like you have given a architecture and you have been provided by the input, so x can take multiple values, so it can take 0, sorry, 1 0 minus 1, so x has a value of 1 0 minus 1, right? And you have, let's name it n1, and let's name this node as the n2, and let's name this node as the n3, and we are provided that there is a bias of 1 in this node n1, and there is bias of 2 at node n2, and you have node n3 as well. So n1 is basically is equal to wx plus b, where you have been provided weights, so w weights are 1 minus 1 and 2 input is 1 0 minus 1. If you do this computation, it will turn out to be 0, right? If you want, if you check n2, the weights are 0 1 and 3. If you do the multiplication with the input, it turns out to be minus 1. n3 has values 4 and 2. If you these are the weights, and the input is coming out into n3 is 0 and minus 1, so 4 into 0, 2 into minus 1, plus n3 had a bias of 7, n3 has a bias of 7, plus there is a skip connection which is coming from x1 to n3, right? So you are adding 6 as well, so the total number turns out to be 11. So there was one more option in this case, which says that like n3 is equivalent to basically uh, n3 can be expressed as a neural network with single layer. The network can be represented using a single hidden layer with one neuron. So that's the case? Because there is no nonlinearity. So if you want to write the expression of n1 is basically w1 x1 plus b, n2 is basically w2 x plus b, n3 is basically w3, which is weights, these weights, time input n1 and n2 plus bias plus x1 term, right? So n3, if you want, you expand it, you just feed the values of n3, these values to here. What you get is basically w3 into w1 x plus b, w3 into w2 x plus b. You get w1 x1, w1 w3 x, w3 basically multiplication of this, w3 x2 x, this multiplication plus bias, and you have a input which is the skip connection x1. So what I've done is like I have extracted out x from this. So you have w1 x3 plus w2 x3 into x. You have 2 w3 b plus x1. So what I have done is like I have written these weights as delta, this factor as beta, and you have the additional term which is x. So what you can do is like it's basically a single neuron, right? Like as there was no non-linearity, it is can be simply expressed as a single neuron where x input x is multiplied by delta, you have a bias which is multiplied by beta, and you have additional x1 term, and you are providing a y as y. So whole network can be expressed in using a single layer neuron. So that's why the nonlinearity is essential whenever you're trying to learn some complex boundaries. This nonlinearity is basically helps. So the next question was related to convolution neural network, where you have an input which is I, you have a kernel which is h, you have a 2 cross 2 kernel, we have 4 cross 4 input. Let's see what should be the output in this case. You have output should be close to 2 cross, it should be 2 cross 2, right? And what you have to do is like you have to compute the convolution operation between I and h. So if you do a convolution, what you do is like you place this value on top of this. As the stride was 2, stride is equal to 2, what you do is like once you place this here, you move 2 steps. So you move here, you are at this point. Similarly, you do this convolution, you do this convolution, right? And when you do a convolution operation, it turns out to be 3 1 minus 2 and 3, right? So the next task was like you apply a nonlinearity or an activation function which is leaky ReLU. And how do you define a leaky ReLU? For values of x greater than 0, it is same. Let us see, it should be like this, but for values less than 0, it is c time x. It should be something like that, right? And c is 0.5 in our case. So if you apply leaky ReLU on z, it turns out to be 3 should be same because it is positive, 1 should be same because it is positive greater than 0. What will happen to 2? 2 will become basically 2 into 0.5 5, that is minus 1. So this has become minus 1 and 3 is same. So the you do addition, this becomes cancels out and the output becomes 6. So the question was actually to what is the sum of your output. Makes sense, right?
Yeah. Sir, one question.
Yes.
When we have our um, this non-linear problem, and when we need to introduce non-linearity, so we have non-linearity functions for activation like salt, sigmoid, max, and ReLU, and this 10 hyperbolic.
Yes.
So, how to judiciously decide about considering which non-linear function among these available functions for faster convergence so that a better non-linearity can be introduced.
Okay, yeah. So what people generally do is like the typical uh, case is uh, they try leaky relu. Leaky relu inside the network. In the output layer, generally do some sort of a sigmoid or yeah, I think the sigmoid is used, or maybe softmax people use it for if it's a classification problem. So leaky relu is something which is very common. Relu you can actually try. So whenever I build any network, I start with relu. If you see that like the model is not training, then you can actually switch to leaky relu. Because what will happen in relu is like there are many dead connections. Because what will happen if you initialize it in a way that like lot of values are less than 0, it makes lot of neurons 0. So basically all the neurons are lying in this region instead of this. So the learning basically stops at this point, because once the neuron is 0, you need some information or like some push to make it move it towards 0. But as this is basically a multiplication operation, so dead neurons remains dead. So that's why the concept of leaky relu was introduced. So the rule of thumb is try relu. It works for most of the cases. If in your case, if it is not working, try leaky relu, and in the output you can try sigmoid, softmax, something like that.
So that means in our learning model, we need to have a kind of adaptive approach. If initially we are not appearing to be converging, then we should switch over to another nonlinear function and
Uh,
then go ahead with computation.
yes. I mean, uh, that is typically the case. I mean, but there can, if there is no learning is happening, then there can be multiple factors. So activation function is just one of them. So you might need to check the losses, you might need to see if we are basically updating the weights, um, if you might see that if your model is capable enough, so there is no case of underfitting. So those things I think you might have to see, but activation functions is just one of them. So I mean many factors are involved.
Uh, Noted.
Yes. Okay. Okay. So moving to the next question. So next question was like you have certain input. Uh, you have suppose have a two-layer neural network. In the output of second layer is Z, which is being fed to softmax layer, right? And what you want is you want what should be the derivative with respect to, let me just see. So what you want is basically derivative of y with respect to z, right? So this what in this problem what you do is like you first define what is the softmax. The softmax can be defined as the e to the power of zi, let's say for ith instance, and for all. So suppose there are j such neurons, and for ith neuron, softmax is basically e to the power z of I divided by sum of all the zi, right? So it's basically in the form of a by b. And if you want to compute a derivative of a by b, what you do is like b into a dash minus a into b dash by b square. This is I think we study in, I think, 12th or something, right? So similarly what you do is like here a is e to the power zi, b is summation of e to the power z j, sum over j. So what you do is like you multiply b, compute the derivative of e to the power zi, it is same as e to the power zi. You like multiply by e to the power zi, compute the derivative of summation operator, and you have a b, like b square at the bottom denominator. So how do you compute the derivative of like summation operator, right? So derivative of all the values with respect to I will be 0 because there is no uh, correlation, right? Only the value which will be one, which will be influenced will be its self value. So self value. So the derivative becomes e to the power zi into e to the power zi. So from j is equal to 0 to n, only value which is relevant for this is basically e to the power zi, right? So what you do is like you extract out e to the power zi from both the terms. So it is here, and you have, what you have is summation e to the power zj minus e to the power zi divided by like square of summation operator. So what I have done here is like I have like multiplied factored basically the denominator with the numerator into two parts. So you have first part is this, second part is this. So this is basically softmax operator directly, and this, if you look, is basically 1 minus softmax operator. So the derivative becomes y hat into 1 minus y hat. Does it make sense?
Yes, sir.
Okay. Okay. Yeah. So this fourth question is basically similar to what you were asking. So you are training a large feed forward neural network with 100 layers on a binary classification task. You are using sigmoid activation in the final layer and a mixture of tanh and ReLU activation in the other layer. You notice that the weight of a subset of a layer is stop updating after few epochs, even though your network has not reached the convergence. Deeper analysis reveals that the gradient of these layers are completely or almost goes to zero very early in the training. That's why there are no updates. So that is the case with the ReLU, right? Whenever there's a if the initialization is or the initial weights becomes negative, it makes lot of neurons zero, which is called as a dead neuron problem in the ReLU. That's why people actually moved from ReLU to like leaky ReLU problem.
Leaky ReLU, yes.
Yeah. So only answer that contains is basically 2 and 3. So uh, what batch normalization does is it basically ensures that there is no deviation in the batch as compared to the overall like mean information which is coming. So so that like what it does is basically that each batch has some sort of a similar information in term of similar mean information. If there is a deviation, a large deviation, it's called as the covariate shift. Batch normalization takes care of that. I think there is a very good paper on batch normalization. Uh, I think that is something like which is very useful whenever, like, if you wish to study.
Okay.
Yeah. Uh, right. So the next is basically you have two multi-layer perceptrons given in figure 1, where all the layers are used linear activation. Which of the following statement is true? So first one is like A is less prone to overfitting since it has fewer connections. So there is a talk about number of connections. Number of connections is basically parallel to the number of parameters. So let's compute what are the number of parameters in A. So you have 100 input unit, you have 100 output units, and you have connections between each input to each output. So you have 100 cross 100 parameters in this case, right? What what do we have in uh, architecture B? You have 100 like neurons in input layer. You have an intermediate layer which has 10 neurons. So 100 is mapped to 10, then again 10 is mapped to 100. So what are the number of parameters? You have 10 into 100, and sorry, 100 into 10 and 10 into 100, so total 2000 parameters here. Whereas in the like the figure 1, network A, you have 10,000 parameter. So the number of parameters in A is way less than the number of parameters is in B. So A has lesser number of connections, right? And this architecture is called as the autoencoders. So autoencoder, what it does is it maps input to the input space only with a bottleneck layer. So this sometimes we call as the latent vector, sometimes we call as the bottleneck layer. But when you are basically doing a squeezing operation where you are extracting out only the important feature which are essential to reconstruct the input, right? So input and output. So it's what is it is doing here is it's basically extracting out only the input or very relevant information which is required to reconstruct it. Because of this bottleneck like architecture, you can only learn limited like parameters here. So suppose you have a 64 dimensional latent vector. So only these whatever it will be learning will be like very crucial and gives a very good insight about what the image contains. Because if you see an image, there is a lot of repeated content in it. So suppose you are looking at an image where the person is standing like below a sky, so the sky has the same color. So you don't need lot of pixels to represent us like sky. So once you have a sense that like there is a sky, you can just extract out like remove all the information and just keep that there is a sky. There are other factors which we might you want to consider, like what the person is wearing, whether the person in what position the person is standing, is it male, female, is what type of age the person is, so that you can actually reconstruct. So this latent vector basically take care of that. So network B is basically some sort of a autoencoder based architecture. Any doubt in that, or like should we go ahead?
Sir, how to determine size of this bottleneck layer that in between to make the network more efficient? Are there any criteria?
I mean, there are papers which actually talk about it. Um, like what should be the optimal size of the latent vectors, but whenever you are training, you generally like do it in a heuristic manner where you say start with somewhat smaller, and if the model is not able to capture the complexity of the data, you keep on increasing the latent representation, latent layer.
Okay.
So there is no like direct way of saying what should be the optimal size of the latent layer. Yeah. So the task is basically some sort of a under representation of features, so that like you can actually extract out the most relevant information.
So that means depending on complexity of the problem, we can apply initial heuristics, and
Yes.
based on that, we can go with some sort of intuitive assessment and decide the size.
Yes, yes, that's true. That's true. That's what. So there is like one. There is no one size fit all problem. So
Yes.
all the like all the different data sets have different approaches. So you might need to see kind of what kind of latent representation, what size of the latent representation fits your data. So if you look at the MNIST data, which is basically black and white images with the counts, that is very simple. So you can have a latent dimension of 2. But if you look at like the cases where there are natural images, there is so much complexity in the image where many objects are present, many backgrounds, there are correlation between the objects. So because the glass is on the table, so that kind of correlations also the model has to learn to reconstruct. So the latent amount of the size of latent representation should be like a larger in that case.
Yeah, I think for feature extraction, if complexity of the image or input is more, as you told, then I think the size of this has to be increased accordingly to capture all necessary features.
Yes. Yeah, so the question 6 was like you have, suppose you have input metrics of A B C D E F G H I. You are basically multiplying with the weights, and you're applying some sort of a non-linearity, some activation function. You get output A B C D, right? And you do a max pooling. In the max pooling, you say that like C, the activation of C is greater than A, B, and D. So the maximum value you are getting is for C. So as we have seen that the max operator basically routes uh, routes the gradient to the what do you say to the region where it's getting the activation. So what it does, like because C is the highest, the gradients are back propagated in this manner. So you have your gradient will be updated for W21, and W2 is triggered by DC DEGH. So that's why only these variables should be like will be used for the update. So that's why like you will see the answer is only dependent on this D, E, G, and H. So the max operator basically routes the gradient in the direction where it's getting the maximum input. As the input was getting from C, it routes it back to the original operators here. So the seventh question is like for a CNN with three convolution layer, each has a 3 cross 3 filter, zero padding, stride 1. What would be the effective receptive field? I think we have discussed the receptive field earlier, right? So what is happening here is what they are asking is like suppose you have a 3-layer neural network, and for each layer what is happening is like you have a 3 cross 3 kernel. 3 cross 3 kernel is there, and what you do is like suppose in the formula which we have derived was right, like you have n is the filter size, s is the stride, and m is your number of adjacent kernels, adjacent pixels, right? So in this case what will be the number of adjacent pixels, because we are looking at 3 cross 3 kernel, you have 3 is basically your filter size, you have 1 is your stride, 2 as the number of adjacent pixels, so it turns out to be 3. So for from layer 2 to layer 3 to layer 1, the receptive field is 5 cross 5. When we move a step back again, right, so it is, if you are like you have filter size of 3, stride of 1. In this case, previous case, you have 5 adjacent pixels, right? So 5 minus 1 is 4, and you have a 7. So this receptive field is 7 cross 7 in this case, right? So in the earlier as well, we have discussed that like creating a deeper network with a smaller filter size is beneficial whenever, instead of creating a like filter which is at a higher size. So 7 cross 7 has a 49 parameters, whereas we are basically using 3 cross 3 kernels. So 3 cross 3 cross 3, 27 parameters we are using to get the same receptive field as compared to what we are getting for 7 cross 7. So it is a more efficient way of designing the neural CNN space architectures. So moving to the next question, so determine what would be the determine what the following recurrent neural network computes. Find what is computed by the output unit in the final step. Take all biases to 0. Assume the input is integer valued and the length of the input sequence is even. The output activation function is tan h, right? So the output activation function is tan h, which is multiplied by 10 times the hidden unit, ht hidden unit, and we are basically have an input which is multiplied by 1, and there is a recursion at with -1. So at ht1 is basically equal to x1, right? This is the first input we have given, and it is been like placed in the hidden layer. You have in the next step, what will happen is, because the ht is multiplied by -1, so now the output will be h. So the next step will be h2, which is dependent on x2. So you have a sequence of input which is coming x1, x2, x3, x4, and so h2 will be dependent of x2 minus h1, right? You have a multiplication of -1 this case. If you feel what is the value of h1 in this case was x2 minus x1. Similarly, when we go one step ahead, so what is the h3? It is dependent of x3 minus h2. If you field what are the values, x3 minus x2 plus x1, right? And what you have to say that like the input is integer valued and the length of the input sequence is even. So we have to consider only the even valued. So h of n is basically dependent at nth step. It is basically dependent on -1 to the power of I xi. So you will be keep on adding xi at each step, and you do it for n steps. So when you do is like when you kind of replace this ht with hn, you get this response. So the answer, I guess, is first one in my case. Yeah. So the next is, which of the following statement is true regarding RNN? So the hidden state has a summary of all the information till time t. That's true, right? Like, because there's a shared hidden representation, and we are updating the hidden representation at each time step, right? Input to the RNN will always a vector corresponding to a text. You cannot feed directly a text information. It has to be in a vectorized format, right? For image captioning, the encoder is RNN and decoder is a CNN. So the captioning is basically whenever given an image, you are basically providing what are the content of the image, like some sort of a summarization or like generating some captions. So the input is a CNN and the output is a RNN. Consider four different versions of RNN, A, B, C, D. There are some of the applications of RNN. So for what you do is like for language translation. So for language translation, there is it is many to one mapping, many to one or one to many mapping as well. So there can be, so suppose there is one word which can be written in English using one letter, one word, but in some other language it is basically two words. So maybe English to French translation. So in that case you need like it's a one to many mapping. Similarly, there can be a case where there are two words which represent the same meaning but can be mapped to a single word in the another language, which is many to one mapping, right? So that's why you need to have some buffer of number of inputs which the model has seen. Then you start predicting. So you also get some sort of a context also, because there are some words in English which can have multiple meanings. So bank has a different meaning. So whether the bank we are talking about is about like cash or like or river bank. So you need some sort of a buffer to start predicting the next like some sort of a translation, right? So it's a encoder decoder kind of architecture only, but you are providing like text in the input and the text in the output, but you do it after some like t steps. For language classification, sorry, video classification, it what it requires is like it need to see certain frames, and you need to have one output, and that will be used by a CNN, or sorry, like a fully connected layer to predict the output, right? So you see like from t minus n to t frames, and then you see that what kind of activity is happening in the video, so that like you can actually do a video classification. In image captioning, what is happening is you see a image and you can have multiple outputs. So suppose there is an image of a boy in with a dog. So this only one input, and you have the boy standing next to the dog. Language modeling is, I don't know, it's not very clear to me. What does the language modeling mean? Maybe some sort of a training. In that case, like you can actually do some sort of a next word prediction task where for an input you provide the output should be provided to input. This kind of modeling is basically a next word prediction task. So you provide I, it should output am should be input. I am walking should be the input, walking here, next word should be to. So maybe that's what the question meant. uh, so there can be multiple form of RNNs, and depending upon your application you should be able to see what is the appropriate architecture. I think I have a notebook as well. Let me see if we can just quickly share it. Can you see my screen? Not this one. Just sorry. Stop presenting. Yeah, so I think this week you guys are actually like learning about the low level features. So like in the previous like before the deep learning era started, people were actually computing these filters, and there was a research topic where people used to identify new filters to extract out important information. So like one of the main features was like how the edges are like represented in the image. So there is some sort of filter called as the Sobel filter. So it's basically used to extract out the gradient between horizontal and the vertical edges. So if you have an image, so there is a function which is present in OpenCV. So cv2.sobel actually does the task for us. So what you do is like you have for the same image you have horizontal gradients, vertical gradients, and you have the overall gradient which is based on the magnitude of uh, x and y. So people used to extract out like identify these feature filters to extract out this edge information, where this edge information can be used passed on to some sort of a classifier like SVM or something, which is able to see whether the image contains a dog or a cat. So the pattern recognition was uh, basically driven by manual feature extraction. But like over the time people have like moved to DNN based deep neural network based architecture, CNN based architectures, where these features are automatically learned by the model. So if you look at the initial layers, the features which are being learned are basically edges only. So edge is some sort of a texture information. So suppose the cat, maybe some sort of ears, or some like what is the color of eyes. Those kind of features are being learned it's by like DNN architectures itself. So like the world has moved, or the field has moved from the handcrafted features to the learned features. So but if you want to provide any in what cases, like suppose you specifically want your model to focus on these features, what you do is like you can actually extract out features using a canny or a Sobel filters and pass it along with your image, so that your edges are highlighted and model is able to learn those edges. This is typically done in the cases where there is the boundaries are not like very clear, and like there is very low like maybe in medical images where the cells are very close to each other, so that like some sort of a gradient information will give the information about the boundary. So in those kind of cases you can actually feed your these gradient maps along with the image to the network which you are training. So I hope in that case the features which are learned are somewhat better than what these like these models are learning. uh, yeah, I think this is all I have for this session. If you guys have any doubt, I think this is the good time you can actually talk. So this session actually we did mostly for like problem solving. We seen the gradient computation. We have seen the how do you what's the effect of receptive fields. We have seen what are the like basically some question all the questions from the assignments, and some low level filters which was discussed this week. Maybe what we can do is like in next session we'll talk about line detections and uh, how like maybe visualize the resonant features, low level resonant features, and draw some similarity between the handcrafted features and learned features. If you have any doubt, please let me know. Any feedback as well, any doubt, anything, it's a good time. Hello, am I audible?
Yes, sir.
Okay, okay, okay. I mean, any doubt, or like, shall we close it here?
my side, it's okay, sir.
Okay.
Thank you, sir.
Okay, okay, thanks. Thank you so much.
Thank you, sir.
Thanks, okay, thanks. Okay, we'll close it here. Okay, thanks. Thank you so much.